Hello everyone. My name is Atreya Vedantam. I am doing BTech at Electrical Engineering in IIT Madras. My JEE Mains rank was 221. My JEE Advanced rank was 315. In the last session, we did half of the chapter of electrostatic potentials and capacitance. So we have finished we have finished the topic of potentials, and today we'll be continuing with capacitance and conductors. So we'll also be solving a few problems at the end of the chapter to get a feel for how problems may be approached in this domain. So we left off with potentials, what potential was, why potentials make it easier to handle than fields themselves, and so on. We looked at dipoles, torque on dipoles, the potential of a dipole in a external field, the potential due to a dipole on any other point, all of these things. So today we look at a conductor. So I think a conductor, everybody has been taught since the 9th grade or so. So there are conductors and insulators, two different types of objects. And the difference between them is that they conduct electrons. So in the case of electrostatic, we will confine ourselves to conductance of electricity. You have heat conductors and insulators as well, but that is a topic for another time. So here in a conductor, when we colloquially say that a conductor conducts electricity, what exactly do we mean? Well, we might know that electricity is really current, and current is the movement of electrons, right? So essentially what we're saying is that there are electrons available in a conductor that are free to move. And this is roughly true. In a conductor, the main difference between a conductor and an insulator is the presence of free electrons. So let's not get into exactly why this is the case. This has to do with energy levels in the atom, quantum mechanics. But the point is, the valence electrons of this atom are hardly bounded by the nucleus of the atom, and therefore they can jump between atom to atom. So this is a sort of misconception when people think of free electrons, as in they're not actually free. They are not free in the sense that you and I are free to move about wherever we want. In fact, technically, if you think about it, you and I are not free either. We are confined to our houses, or at least a monetary limit on where we can go, right? You are not free to travel anywhere you want. In fact, none of us are probably free to travel to, say, another planet, right? So even though we feel like we're free to travel somewhere, there is actually a pretty big locational constraint that we are unaware of. And in a similar sense, these electrons are not free to go anywhere that they want. They're free to go to any outer shell of an atom that they want. And this is roughly free enough. When we're talking about reasonably sized object, there are trillions and trillions of atoms. So this is hardly of any consequence, the fact that they're not completely free. So they can just consider them to be a sea of electrons floating around in an object. So the free electrons, the textbook says that the free electrons form a kind of a gas. They collide with each other and with ions, and they move randomly in different directions. So it makes no sense that they would follow a certain direction. They all follow random paths. In a couple of sessions ago, we saw about the kinetic theory of gases, and we saw how gas molecules can be, modeled. Gas molecules behave. Have very random velocities if you look at it on an individual scale. But the purpose of the kinetic theory is that we look at statistical averages and make predictions based on it. So there's a little bit in this textbook about charge carriers, which is what the point that I was trying to drive. But let's not go too much into it. There are a few properties of conductors that are very important, so we'll go over them. So the first point is that inside a conductor, the electrostatic field is zero. And there's actually a very intuitive reason why this is the case. And I spent some time on this. So let us take a conductor. So here, this is the random shape of a conductor. And as I've discussed before, the electrons here are roughly free to move everywhere, because on a macroscopic scale, it really doesn't matter that they can't be inside the atom. So there you go. So these electrons can move anywhere that they want. Now let us say that the electrons were in such a way that there existed an external electric field. Okay. So there is an external electric field, and all of these electrons are scattered inside the metal. Now, if the thing is, because the electrons are like this, they're free to move, right? So the external electric fields, this field that's caused by these electrons is going to move them around. It's going to drive them around, right? So, but then the moment that they start moving around, they are no longer in this position. So the very fact that an electric field can move these electrons around means that the electrons have to be on the boundary of the conductor. Then the moment that they're inside the conductor, they're free to move and they get kicked off to the boundary. So basically that is the intuition. So as long as the electric field is not zero, the free charge carriers would have to experience some force, and so they drift. So the way the charge carriers are distributed themselves is to make the electric field zero. Only then since the field will be zero, none of the electrons will experience any force, and this would be an equilibrium state. So of course you might argue that when you make a conductor immediately, of course they take some time to move around and settle into their equilibrium state. But actually this time is of the order of nanoseconds or microseconds. So it really doesn't matter. After 2 or 3 seconds, you can assume that they are practically in their equilibrium state. So that's an important point. The second point is that at the surface of a charged conductor, the electrostatic field must be normal to the surface at every point. Remember in the last session, we discussed about why electric field should be normal to the equipotential surfaces. And it's a very, very similar argument in this case. Let us say that on the surface of a conductor, the electric field had a tangential component as well as a normal component. Then this tangential component of the electric field push these electrons around. And because they are free, these electrons will move. So that is the important distinction between this argument applying to conductors and insulators. The issue is you can apply the same argument to insulators as well. But the only problem is whatever argument you're making will fail at the moment of the electrons actually moving around and being influenced, because the electrons in the insulator are simply not as free. So the only difference is in a conductor, these electrons can actually move. So whatever external electric fields that you have to move them around will actually influence them, will actually end up influencing them. And because of that, since you can't have that, because we're looking at an equilibrium state, the electric fields have to be normal to the point of the surface of the conductor. Okay. The interior of a conductor can have no excess charge in the static situation. So this is what we just discussed. So why can't it have charge? So we've seen from the first property that the electrostatic field at all points inside the conductor is zero. So let us say that there were a few charges, plus, minus, okay, inside the conductor. But we know that from the first property that the electrostatic field is zero. Now consider a very, very small Gaussian surface around one of the charges. Since the charge enclosed by this very small Gaussian surface is non-zero, the electric field also must be non-zero at some point in the surface. Otherwise, you cannot have a non-zero flux, which you clearly do since you have a non-zero charge. So this results in a contradiction to the property that the electrostatic field must be zero at all points in the conductor. And because of this argument, there can be no charge inside the conductor. So all charges reside at the surface of the conductor. Now, the argument for cavities is basically the same thing. We look at what happens when you have a cavity inside a conductor. Yeah. So okay, the third property is that so we looked at the third property. The fourth property is that the electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. This should be intuitive because we've looked at a very similar case in the case of a hollow, uniformly charged sphere. The electrostatic field inside the conductor is zero, right? So because of that, your integral E dot dl is zero. As in, the change in the potential, as we looked for the definition from last session, is the integral of E dot dl with a negative sign from point A to point B, right? Now, if the electrostatic field is zero at all points, this integral is clearly zero. So the change in potential is zero. So the potential is the same throughout any 2 points in the conductor, which means the potential is the same at any point in the conductor. And the second part of the property states that it has the same value as on the surface of the conductor. This is slightly trickier to prove rigorously, and it would require something called boundary conditions. What are boundary conditions? So this is basically saying that the potential is not discontinuous across the boundary, right? So you can see that it has the same value on the surface as it has on the inside of the conductor. That is basically saying that if it has a potential of like 4 volts roughly just inside the conductor, then on the surface also it has 4 volts. It is not suddenly jumping to 6 volts or dropping to 1 volt. There is no discontinuity of potential. So it's a trickier argument to make. But yes, but if you think about it, the electric field has a finite discontinuity. So intuitively, the potential should not have a discontinuity, right? It is of course non-differentiable because after just outside the surface, it starts dropping off as some 1 over r or 1 over r power alpha, depends on the charge distribution. But inside it's constant, so you can see it's non-differentiable, but it is continuous. Okay, the fifth property is that the electric field on the surface of a charged conductor is sigma by epsilon naught n cap, and this actually is follows directly from the Gauss's law. So you can see this diagram here. So if you have a very small surface dou s, and you know the electric field is normal to the surface. So E dot dou s is equal to whatever the surface charge is at that point, which is sigma, times dou s, which is the charge, by epsilon naught. This is Gauss law, right? You cancel dou s on both sides and you find out that electric field is sigma by epsilon naught. Okay, and now we come to the sixth point, which is probably the most important point in a conductor: electrostatic shielding. So if you the basic point of this property is that any metal, if you have a cavity inside a metal, then let's say this is the part inside the cavity and this is the universe around the metal. So the red is the cavity and the blue is outside the universe. This property is basically saying that the red and the blue parts behave as roughly independent universes. They do not affect each other in the sense of electrostatics. That is because any variation inside the cavity is taken care of by the charges on this surface, positive or negative. And any disturbance in the universe around the metal is taken care of the charges on the surface of on the outer surface of the conductor. And therefore, neither of these two cavities or the universe outside influence each other. That is the property. So we will not do the proof here, but the point is that the charge distributions on any given surface take care of all the electric fields and basically make the electric fields inside the conductor zero, right? So inside the cavity it's not affected by what happens outside. What the charge distribution is outside the conductor. So this is called electrostatic shielding. Okay. In other words, if there is no charge inside the cavity, then you know that the electric field is going to be zero inside the cavity. So that is what the textbook is saying, and it's basically rephrasing what I'm saying. So the electric field is inside the cavity is always zero as long as there is no charge inside the cavity. That is what electrostatic shielding is saying. The metal shields the cavity from the rest of the world. Okay. So now there is actually one more point that I'd like to mention that's not there in the textbook. The seventh property of a conductor is something called the uniqueness theorem. It's a very interesting theorem, and the proof of this is beyond the scope of what we are doing in this session. But the point of this theorem is that the charge distribution around on the surface of a conductor to make the electric field inside the conductor zero is a unique one for a given electric field. It's a very bold statement. It is saying that there is no other charge distribution. There is no other way that these positive charges and these negative charges can be placed around the conductor such that the electric field is zero inside the conductor at all points, except for one such distribution. So it's a pretty remarkable statement, right? That's what uniqueness theorem means. So it's saying that there's a unique solution to this problem of making the electric field zero inside the conductor. It's probably not very practical. You might not get asked questions on it, but it's a useful fact to keep in mind. So next we come to dielectrics and polarization. So a dielectric is so what happens is we have seen that in a conductor the charge distribution. So you can see in the diagram that if you have an external electric field E naught, the internal charges distribute themselves along the surface such that they exert an internal electric field such that these both are equal, right? That's the purpose of that's what these charges are doing. The charges distribute themselves in such a way that their electric field that they exert, which is in this case E in, should be equal to the E naught, which is the external electric field, magnitude wise. Only then can the electric field inside the conductor be zero at all points, right? But a dielectric is basically a dumbed down version of a conductor, right? So what happens is the induced electric field, which is represented by E in, is trying to do something trying to do what a conductor does, but the charges are simply not as free. And this induced electric field, therefore, is not as strong to completely quell the effect of the external electric field. And therefore, instead of completely making the electric field vanish, it only minimizes the electric field. This is called a dielectric. So, how does this dielectric work? Well, you have something called a dipole moment, right? You have polar and non-polar molecules. Hydrogen, H2 and CO2 are non-polar molecules because they're symmetrical. And in the case of hydrogen, there's no polarity, there's no electropositivity and negativity difference. Whereas in molecules like HCl and water, you have a dipole moment because they're either non-linear or they have a electronegativity difference. So because of this dipole moment, when you have an external electric field, all these polar molecules align in a fashion to induce a electric field. So this is what polarization is. So think about the English word. Colloquially, where would you use polarization? Well, you would say that a group of people are polarized into doing something. So what does that mean? That means that individually people have their own opinions and expressions, but in the context of handling a certain issue, if they're all united in one goal and they want to work for it, say strongly, then you call them polarized, right? In a very similar sense, when all these molecules, when in the presence of no external electric field, they would just be scattered around, pointing in random directions, and therefore contributing to no significant macroscopic effect. In the presence of an external electric field, they all decide to gang up and align themselves, add their individual contributions, and make significant induced electric field in the opposite direction to diminish the value of the overall electric field. So there you go. This is a very good diagram of what's happening. You see that all the molecules are in the same direction. They are polarized. So this is what it's called polarization. So yeah, and if you remove the external electric field, very interesting things can happen. These molecules which were polarized can suddenly again come back to their randomized behavior, or they can stick to where they are. And depending on these differences, the materials can be further classified into paramagnetic, ferromagnetic, and diamagnetic. So here we make a very important assumption. So you have something called a polarization vector. Okay, the polarization vector determines how much how much the molecule has been polarized, and this is a function of the electric field, external electric field, right? It makes sense that if the external electric field is zero, then the polarization would also be zero because all the molecules are random. However, if the external electric field would be in a certain direction, then all the molecules will be polarized in some direction. And these two directions need not necessarily be the same. That's actually a very important property. A point to note. It's a good point to know. So there are dielectrics. We will confine ourselves to what are called linear isotropic dielectrics. These basically what this is saying is that the direction of the field and the strength of the field is proportional to the polarization. So what we are saying is that polarization vector is some constant times the electric field. So the external electric field. So the polarization is proportional to the electric field and is in the same direction. And usually we call this constant chi. Okay. So we call this electrical susceptibility. So you'll see this soon. This need not always be the case. In fact, for a more general class of problems, you'll see that the magnitudes are actually proportional, but the directions need not be. And in that case, chi will not be a scalar, rather what is called a second rank tensor, but we will not get into that. So here you see that the polarization P is equal to epsilon naught chi E times the electric field, where chi E is called the electric susceptibility of the dielectric medium. So there you go. So you see that the external electric field is this way, and all the molecules are polarized in the same direction, right? So that is the thing. Okay, now at last we come to capacitors and capacitors, the next topic. So what is a capacitor? So now that we looked at what a conductor is, the simple way to construct a capacitor is take two conductors. They can be of any shapes. Conductor 1, conductor 2. Okay. Put a charge of positive charge Q on one. Put a charge of negative Q on the other. Okay, and let them distribute themselves and bring them near each other. That's it. It's called a capacitor. Okay. So these two conductors have a potential difference. What does that even mean to say? So I remember when I was studying, I had this big confusion. Potential difference between what 2 points? I mean, these are very clearly very big bodies. They're clearly not spherical. They have a weird shapes and they have a weird charge distribution. So shouldn't these potentials like vary widely depending on what points you take within the conductors? That's a doubt that I had. And the answer is no, actually. The reason you can speak of a potential difference between the two conductors themselves is because all points inside the conductor have the same potential, right? You've seen that property before. The electric field inside the conductor is zero. So therefore, all points inside the conductor have the same potential. Therefore, the potential difference between the conductors can be thought of as a single quantity between any 2 points, right? So this potential difference is called, you denote it by V1 minus V2. And it so happens that the greater this magnitude of the charge, that is, if you double this charge on conductor 1 and you make the negative Q double, like in minus 2Q, then it so happens that the potential difference also doubles. And therefore, you can define a constant which is Q by V. And this constant is called the capacitance of the conductor. So the ratio Q by V is constant, it is called the capacitance. We'll soon look into what capacitance actually depends on. It depends on the geometrical configuration, that is the shape of the conductors, the sizes of the conductors, and the separation of the conductors. It also depends on the nature of the dielectric separating these two conductors. So yeah, there's a point I've forgotten to emphasize properly that I think requires emphasis is the nature of the medium between any two bodies in electrostatics. So whenever we have talked about two charges attracting each other or repelling each other, what we assume is that they are all in free space. That is, there are no other external fields, there are no polarization, there are no molecules around. But if you do any experiment in the real world on Earth, then you're going to have molecules, right? You're going to have polarization and other effects like that, and we have to take those into consideration. So, at this point, I think I'll clarify a very important misconception. So if you look at you can be asked questions like, what is the force between any two charges, given that there is a dielectric between them? So there is some polarization happening between these two charges. So that is going to affect the electric field, right? We have seen how polarization can reduce the overall electric field, not as effectively as a conductor, but to some certain extent. So if there were a polarized medium somewhere here in between these two charges, would that affect the force between the two charges? So it depends on what question you're asking actually. So the question is, is the force between the two charges changed? The answer is no. The Coulombic force is always 1 by 4 pi epsilon naught Q1 Q2 by R squared. So this is not at all dependent on the medium. So whenever you're asked, is the force between two charges changed due to any sort of medium? The answer is strictly no. It remains 4 pi epsilon naught. It does not become 4 pi epsilon as some people might think. However, if the question were, in the presence of the dielectric, what would be the force on one of the charges? That would be 1 by 4 pi epsilon Q1 Q2 by R squared. The reason is this polarization, the polarized medium does not affect the Coulombic force between the two charges themselves, but it affects the net force on its given charge. The contribution due to the medium in between affects both the charges, surely. It affects both the charges, but it only affects the net force. So if you look at only the Coulombic interaction between the two charges, that remains independent of any medium that is in between the charges. However, the net force will definitely change. So that is where you should look at the wording, the English structure very carefully. Okay, the framing of the question. So anyway, so we will see that the capacitance also depends on the medium between the two conductors. In this case, this kind of medium. In free space, it is something, and if you have a polarized medium, then it is something else. Okay, so first, why not get a feel for the numbers? So first, we look at units. Okay, the units of capacitance is Faraday. So 1 farad is defined as 1 coulomb per 1 volt. Okay, a farad is a coulomb per volt, and the capacitor is denoted by in this symbol. You know, this is a resistor, this is a capacitor, and you will soon see what an inductor is. So this is a capacitor. So the way this is a representation, because this is one of the positive plates. You have a plus Q on this one, and this has negative Q. Okay, you see it's basically the same diagram in a more represented in a compact way. Sorry. So firstly, Well, even though the unit of capacitance is a Faraday, it's 1 farad, is a farad. The issue is it's very very rare in practice to get the capacitances of a farad. In fact, almost never. In fact, nowadays with modern technology, you're able to get capacitance up to 100 farads in a very small box. So it's quite a miracle. You will only appreciate what a miracle that is if you understand that most capacitors we are going to deal with are of orders of microfarads, which is 10 to the power -6 farads, or even nanofarads, or even sometimes picofarads, 10 to the -12 farads. So if you have, when you see such small orders of magnitudes as on a daily occurrence, it's very very shocking to see something as big as 100 farads. And yeah. So anyway, now we'll move on to the parallel plate capacitor, which is the most important. It's the simplest form of a capacitor, really. So we're going to be looking at it with some detail. So there you have. So a parallel plate capacitor. So what does that mean? Parallel plate. So there are two plates which are parallel. So their AC is on that one plate. That is the second plate. They're parallel to each other. This plate has been given a positive charge of +Q, and this plate has been given a negative charge of charge of -Q. So right, I hope you remember how to construct a capacitor. It is basically two conductors. You give one conductor a charge of +Q, and the other conductor a charge of -Q. So in this case, these two are parallel plates. So naturally, when you do that, these charges distribute themselves on the surface of the conductor, as you have seen in the properties of the conductors. So what do you think is the electric field between them? So that we can easily do by we can calculate using Gauss law. So you have this charge Q, right? And you have an area of A, say, okay? There's an area A. I'm showing you where the area is on the parallel plate. That is the area. It's in 3 dimensions. It's clearly badly represented here. So, so this charge is going to be. Let us define the surface charge density to be sigma equals Q by A. Okay, and now we'll exactly see what we're going to do. So this plate is very thin. Okay, so we are going to neglect the charge that is on this plate on here. Okay, so what's going to happen is this +Q is going to distribute itself as Q by 2 here and Q by 2 here, right? And similarly, this negative charge is going to distribute itself -Q by 2 here and -Q by 2 here, right? So now we can do it 2 ways. We can do it using Gauss law, or we can just use superposition. So what do you think is the electric field this way due to this positive charges, set of positive charges? Well, we have already seen in the property of conductors is that it is sigma by epsilon, right? I hope you remember that. It is the last property in the textbook. So in this case, it is the surface charge density on the surface is Q by 2, right? It's Q by 2 by area, which is A. So basically, it is Q by 2A epsilon naught, right? That is the electric field caused by this positive charge, right? Now, what about the electric field caused by this positive charge? That will be here in this direction and also equal to Q by 2A epsilon naught. Now, due to this negative charge, we are going to see the exact opposite. The electric field caused here will be Q by positive Q by 2A epsilon naught. Why positive? Because I've already marked the direction appropriately, right? And similarly, this is also going to be an electric field of strength Q by 2A epsilon naught. Now, if you use superposition, you will get to see that this electric field, which I've marked with black, encircled with black, is also going to be applied here, right? This electric field carries over all all over here. So this arrow here and this arrow here cancels each other out, and there is no electric field this side at all. The charges are there, sure, but there is simply no electric field here. Due to symmetry, you can argue in the same case, these blue arrows here are also going to be here, and they're going to cancel out with the black arrows here, and there's going to be no electric field here. Whereas inside, they're actually going to end up adding up because they're in the same direction, right? So the Q by 2A epsilon naught becomes double, and therefore the field inside the conductor is Q by A epsilon. So there you go. That's what the textbook also says. So therefore, the capacitance is the Q by B. So, and the voltage is simply the electric field times the distance, because the integral E dot dl is simply E times L, because electric field is constant, right? So in this case, so therefore you can calculate V, and C is simply Q by V, which is epsilon naught A by D. So all right, so now you can actually see that upon actually calculating with some roughly believable values, see, an area of 1 meter squared is actually a lot, right? If visualize it in front of you, it's a lot, it's a big area, right? And that itself will give you a capacitance of 10 to the negative 9 farads. That's basically it's a nanofarad capacitor, right? So now I think you appreciate what it means to have 100 farads. It's a lot. So the formula for a capacitance in a parallel plate is epsilon naught A by D. You will soon see that if there is a dielectric, then a dielectric with a dielectric constant of K, then the capacitance will be K epsilon naught A by D, because K epsilon naught is simply epsilon. Oh yeah, so there you go. You have the same formula here. So I think we've seen that epsilon naught is called the permittivity of free space, right? Well, what the term actually means is that free space is allowing the electric field to permeate its body with that amount of strength, whereas air or water especially is far more reluctant to allow the same amount of freedom. It's basically like a tax law in a country, right? If a country has heavy import taxes or whatever, then then other businesses may not be as willing to settle here. So their strength of business will be smaller in that country. So in a very similar sense, the strength of the electric field is smaller, much smaller in water actually, because the dielectric constant of water is 80. It's pretty high. The dielectric constant of a vacuum is obviously 1. That's what you define dielectric constant as. The dielectric constant of air is very, very close to 1. It's 1.001 or something, if I remember. You can assume it's practically 1 in air. Water is 80. That's very, very high, because water can get really polarized, right? If you think about it, water molecules are polar molecules, right? So when you have an external electric field, they're all very eager to polarize against your sphere, therefore diminishing it a lot. So, okay. So there you go. So K is equal to epsilon by epsilon naught. So epsilon is the permittivity in any medium. So the permittivity in any medium is defined as the permittivity in free space times the dielectric constant of that medium. Okay, now we come to combinations of capacitors. Capacitors in series. So first, there you go. Capacitor series are represented like that, just like resistors in series. And you will come to see that the voltages add up, right? You remember how we argued for the equivalent resistance of a series of resistors? Is that we said that the voltages simply add up, the potentials add up. In this context, I should say potential differences add up, and therefore since the V is equal to IR, the resistances simply add up because the current is the same. Well, in this case, the charges are the same, and therefore the inverses of the capacitance are add up. So 1 by C is equal to 1 by C1 plus 1 by C2. So in fact, capacitors in series behaves like resistors in parallel. And actually, you'll see soon that the vice versa also holds. Capacitance in parallel behaves like resistors in series. And well, the reason is simple. If you look at it, V is equal to Q by C, right? That's how capacitance is defined, right? Capacitance is Q by V. So V is equal to Q by C. whereas V is also equal to IR for the resistor, right? And if you think about it, I and Q behave like each other, right? Because charges are the same in series and currents also are the same in series. So you can see that 1 over capacitance behaves like resistance. So whenever you see resistance, you can replace it as, you can see that the capacitance would behave like the inverse of what it behaves like. Of course, this is not exactly the case, because you will see that capacitors actually follow a something called a phase difference. Okay, we'll not get into this. This will be apparent in electromagnetic induction, that capacitances behave out of with a phase difference of 90 degrees. But in DC sources, you can think of capacitance as behaving like the inverse of resistance. So now we come to capacitance in parallel. It's basically the same argument. In this case, the charges add up, and so therefore you can see that the capacitance simply add up in series. So okay, now we come to the energy stored in the capacitor. So we have seen the electric field inside a capacitor, and how and if you want to find out what the energy is stored in a capacitor, all we have to do is simply add a small delta Q to that capacitor and see exactly how much the energy change, how much work you're doing to add that delta Q, right? That is basically a standard process in the way we calculate energy. Whenever you're looking at, say, the self energy of a conductor, the way you would do that is you have a certain conductor in place, okay? You have a partially assembled conductor. Then what you're going to do is you're going to bring a small delta Q charge all the way from infinity to you to that point to assemble it a little bit more. And the work done to increment the assembly of this conductor, if you just integrate it over all the charge, you will find out that that is the self energy. That is the energy that the conductor has, because that is the work that any external person is doing to assemble that conductor in its whole. So there you go. You see that through some mathematical calculations, that the work done is Q squared by 2C, or that's because Q by C is the voltage, right? And the work done is V dQ. So voltage times dQ. You're integrating over all the charge. So that is simply Q squared by 2C. And Q is equal to CV, right? From the relationship. So therefore, you see that the work done is half CV squared. Okay, so the energy stored in a capacitor is half CV squared. And in fact, we can also derive what the energy density of the electric field is, because you can see that capacitance is epsilon naught A by D, right? So you get this expression. And therefore, if you want to find out per unit volume energy density, the volume is AD, right? In a parallel plate capacitor, the area is A, distance is D. So the volume is AD. So if you divide by AD, then you get half epsilon naught E squared. This is the energy density of the electric field. Now you may ask where exactly this energy is contained, but it turns out in physics that such a question is kind of irrelevant. It doesn't matter where the energy is stored. All it matters is that when you integrate it over a certain volume, you get the total energy. So it so happens that you have to integrate this over the entire free space if you want to find out the self energy of say a sphere. So that's an alternative method. So what I've just described, right? The method of calculating self energy using bringing charges from infinity. That is one possible method. But another possible method is simply to integrate the self energy, integrate the energy density over all of space. Okay, so with that, we've come to the end of this chapter. So now let's solve a couple of problems for a little while. An important, this is very important, guys. Dimension and analysis is very, very underrated. It cannot be overemphasized. I think at every step in problem solving, especially in physics, it is useful to keep in mind what exactly what are the dimensions you are dealing with. When you look at say electric fields, and you come across you say electric field is some 3 volt per meter squared, then you immediately should know that you're wrong, because you should think of appropriate formulae. If you can't remember the direct dimensions immediately, you should think of appropriate formulae. in this case, what should come to your mind is the electric field is negative dV by dx, right? So you can clearly see that dV has dimensions of voltage, dx has dimensions of length. So the electric field should have dimensions of volts per meter, right? So any answer with volts per meter squared should immediately appear to be wrong. So that is one important point to keep in mind. A second important point to keep in mind is order of magnitudes. You should clearly know what orders of magnitude you're dealing with. What does order of magnitude mean? Well, it is roughly the power of 10. So are you dealing with the thousands of quantities? Are you dealing with the millions of quantities? Or are you dealing with millimeters of amounts of quantity or micro amounts of quantities, right? That's very important because you'll understand you can be off by say 2 or 3 in terms of magnitude, in terms of numbers, but you can't be off by 100 times or so, right? That just simply means that you don't have an understanding of what is being asked, right? What sort of answer you're expected to get. So yeah, all of that will help. So all right. So we'll solve a couple of problems. We don't have time to solve everything. So there are 11 problems here. We'll pick a few. So well, if you look at the first problem, two charges are located 16 centimeters apart. At what points in the line joining the two charges with the electric potential 0? So there you go. And we are given that the potential at infinity is 0. So remember, there is no sense in talking what a potential is unless you define the reference potential, because the potential can be arbitrarily increased or decreased. It's only relative. You only look at potential differences. And in the case of finite charge distributions, it is convenient to take the potential at infinity to be 0. I think we have not discussed what happens when you have infinite charge distribution. I think we briefly looked over it, right? You see that the electric field is constant. And because of that, since the electric field is constant over any finite length L, the potential difference is E times L. So now you might start to understand where the problem is. If you say that the electric potential is 0 at infinity, since you would have to travel an infinite length to get to any finite finite distance away from the origin, the potential difference is essentially infinity, right? So that is of very little use to us. So only in such infinite charge distributions do we not take the potential at infinity to be 0. In all other cases, it's convenient for us to take the potential at infinity to be 0. So you see these two charges. So you see that they have magnitudes of 5 times 10 to the power minus 8 and 3 times 10 to the power minus 8. It's always useful to draw a diagram to see how the field lines interact. So there you go. The field lines look like that. And well, you see the field lines emanating from the positive charge want to go to the left, but then the negative charge is pulling them to the right. So you see that the potential should be 0 at some point. So the electric field should be 0 at some point to the left of the positive charge. Whereas the potentials, calculating this superposed potential is a totally different game, right? It's simply the scalar addition. There's no vector addition here. So you see that if you have a positive or negative charge, the potential is clearly 0 somewhere in the middle. So let's say it's at a distance of x. So you simply apply the formula. So q by x plus q prime by L minus x is 0. That's it. L is 16 centimeters. Q is 5 into 10 to the negative 8. Q prime is negative 3 into 10 to the power negative 8, and you can solve for x. It's not a big deal. It's just simply it's an equation in one variable. In fact, I'll just show you the form. So QL minus QX is equal to minus Q prime x. So x is simply QL by Q minus Q prime. So I suppose, I hope you can substitute all the values, where Q is, this is Q, this is Q prime, and this is L. So that should be simple enough. Okay, 2.2. A regular hexagon of side 10 centimeters with a charge of 5 microcoulombs at each of its vertices. Calculate the potential at the center of the hexagon. So, well, luckily, okay, what would you do if you were asked to calculate the electric field? Well, in this rare case, it so happens that calculating the electric field is simpler because of the symmetry. You can argue that the electric field is simply 0 because if the electric field were pointed in any other pointed in a certain direction, you could always argue why not some other direction, because it's perfectly symmetric, right? Or I mean, just look at the, if you want, just look at the field directions at that point, and they all simply cancel out if you look at the vector sum. But in the case of potential, they simply add up because they're scalar, right? So you simply have 6 times the potential as if there was only one charge there. So 6 times kq by r. Sorry, I should not say k. I mean q by 4 pi epsilon naught r. Okay, that's it. I think q you can substitute as 5 microcoulombs. R you can substitute as not 10 centimeters. Be very careful. R is not 10. 10 is the side of the hexagon. Therefore, R happens to be 10. Okay, in this case, it just so happens that they're equal, but R is the distance between the charge and the source, the test charge and the source charge. And for different shapes, that may be different. You should use trigonometry to find out what their length is. In this case, because of the hexagon, they're all equilateral triangles, so all the side lengths are equal, right? That's why it's also 10. But usually it may not be. All right, we will solve, say, one more problem. 3 capacitors are connected in parallel. What is the total capacitance? Well, you have seen that parallel capacitors simply add up, right? So the capacitances of parallel capacitors simply add up. So you have 2 plus 3 plus 4. That's 9 picofarads. The second question is determine the charge on each capacitor if the combination is connected to a 100 volt supply. So you have parallel capacitors like this. And it's all connected to a 100 volt supply. So the potential difference between all the capacitors is 100 volts. So all you have to do is simply, if you want to find a total charge, if you want to find the charge on each capacitor, well, charge on capacitor 1 is simply the capacitance 1 times the potential difference, which is 100 volts. And C1 is simply 2 picofarads. So it is 200 coulombs. 200 picocoulombs is simply 0.2 nanocoulombs, a very tiny charge. Similarly, Q2 is 0.3 nanocoulombs and Q3 is 0.4 nanocoulombs. So the same calculation. Okay, we'll solve the last question. 2.10 say. A 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored in the capacitor? Well, the energy stored is, we have derived is half CV squared. I hope you remember how we derived it. We derived it as voltage times dq over all the charge. Okay. So that happens to be half CV squared. Quick derivation. So this is equal to half times 12 times 10 to the power negative 12. Pico means 10 to the negative 12. Times V squared, which is 2500. So that is 6 times 25 is 150 times 100 times 10 to the negative 12. So that is 15 nanojoules of energy, a very tiny amount of it. Okay, so I suppose roughly gotten the idea of how to solve problems in this chapter. They're not very complicated as long as you remember the concepts. There are a lot of concepts about potentials, capacitors, dielectrics, linear dielectrics, and so on. But as long as you keep in mind the basic properties of electrons, the way they behave around electric fields, the way different materials counteract the external electric fields, right? At the end of the day, electrostatics is all about electric fields and how to calculate the effects on charges. And the entire show business about potentials, voltages, and so on is simply a human invention to help us tackle better, because field addition is far more complicated, and we would just prefer to add up 2 plus 3 plus 4 instead of doing some complicated some x cap plus 3x cap and so on. So, to avoid vector addition, we define, we use potentials to simplify our life. So anyway, that's how you solve problems. And hope you've gotten a better hold of electrostatics, potentials, and capacitors. So yeah, with that, I think we'll wrap up this. Thanks.